you likely have a pretty good idea of what the different variables do to the period. And the period is really a measure of the speed, right? What were the three different things that we changed in our experiment?
Length, numbers, operating rate.
What was the first one?
Well, length of
The radius, right? Yeah. The length of the circle, the length of the string, the radius of the string, the force, the number of washers, and the last one was the mass, right? Okay, so I should probably be able to ask you, if I change this, what happens? And you could probably tell me just sort of qualitatively. So, we're going to take the results of our experiment and derive some formulas that relate to typical force, FC, to various aspects of UCM, the three things. So the first one was period squared versus FC. When you graph the period squared versus FC, your graph should look like this. What did your graph look like? You should have your graph with you. What did your graph look like? I'm going to press click right away, it's going to show up right there. What did your graph look like when you graphed period versus FC? A period squared. Was it curved? Is this the one that was curved? Yeah. So you should have got that. Did everyone get that, every group? It was pretty obvious, right? And as I said before, we generally get pretty good results. So what this suggests, or what this means, is that it may be an inverse or an inverse squared graph. And to confirm this, we're going to graph t squared versus, and I'm missing something, oh here it is here, t squared versus 1 over fc. Okay? And that will tell me whether it's an inverse or inverse square relationship. So you graph t squared versus 1 over fc. And did you get this? Did you get a straight line? Straight-ish. So this tells us that t squared, the period squared, is proportional to, funny looking fish sign, proportional to 1 over fc, which means the bigger the force, the inverse relationship, bigger the force, the starts with small, ends in lure, smaller. The bigger the force, the smaller the period. The smaller the period means that it's moving faster, right? Well, did you find out the more washers you added, the faster it went around? You should have. Right? The low one you could do easy, right? It's harder to do faster. Okay, that's kind of the way they used to do things before graphing calculators and computers. They had to do that sort of graph analysis, do that inverse thing, make the graph into a straight line. By making it into a graph of a straight line, you sort of prove the original one. I'm not going to go too much into that. We use computers now. Computers are good. So we know that t squared is proportional to 1 over fc. Okay. The second one that you graphed was the radius. What did you find? Complete the sentence. The longer the string was, the slower or faster, the longer or shorter was the period. When it was a long string, did it take a long time to go around, or did it take a short time to go around? A long time. Pretty obvious, right? Short little guy goes around fast, right? Even makes that sound sometimes. Long one takes a long time to go around. It's pretty obvious. What kind of graph should that be? Start the clock. Straight line. Did you get a straight line for part 2? Ish? Yeah? This implies that t squared is proportional to r. The period squared is proportional to r. The bigger the radius, the bigger the t squared. What happened when you added mass? The more mass, did it make it slower or did it make it faster? More mass made it faster? And slower means bigger t or smaller t? Anywhere up there is good. Did you get a straight line graph? Nod with me. Yes, I got a straight line graph. Thank you. This implies that the period is proportional to mass. The bigger the mass, the longer it takes to go around. Okay, so that's the data that you guys collected in the form of shape of graphs. I know what they're supposed to look like. You got a straight line. You would have, right? Ish. Some of you would have been straighter than others, but more or less you get that kind of thing. Okay. By combining our proportionalities together, we had 3 separate ones. I'm going to get t squared is proportional to Rm over Fc. All I did was combine those three proportionality statements together. How do you turn a proportionality statement into an equation? Do you know? You might not know. You get exactly the same thing, but instead of the proportionality symbol, you get an equals, and you have to insert the letter K. What does K stand for? It is a constant of proportionality. It's the number that makes the proportion work. You're familiar with this. You've seen this. You probably have been shown that the circumference of a circle is proportional to the radius. The bigger the radius of the circle, the bigger the circumference all the way around. Do you know what the equation or the constant of proportionality is? Actually, I guess maybe instead of radius, you might have seen it more with diameter, right? C is proportional to diameter. What's the number that makes it work? Do you know? I think you do. It's pi. Pi is the proportionality constant there. C divided by d is equal to pi. The Egyptians found that out. When they took the circumference of any circle and divided by the diameter, they always got a number around 3. And the more precise the measurements, the closer they got to 3.141596. That's as far as I go. Now, this proportionality, this equation here can be arranged to, I'm just going to flip the FC and the t squared, okay? Whatever you want. I haven't gotten to the formula yet. I'm just sort of laying the foundations here. It's a long process.
This is important.
What's important today is the process and the end result.
So have we even gone to the process?
All I've done, I've started the process. Let's go back. In fact, I wouldn't write any of this down. I mean, really. Pardon me? If you've started, be my guest, continue. Let's go back and I'll review what I've done. Well, it's not.
Yeah, what if it's long stuff, you know?
Am I going to ask you to derive this formula on the test? No! It'd be insane to do that. I'm not going to ask you that. But I'm going to ask you to pay attention and sort of get what I'm talking about. That's what I need you to do. I gave you one proportionality statement. I said t squared is proportional to 1 over fc, right? That's 1. 1, 2, t squared is proportional to r, and t squared is proportional to m. And then I put them together to give you this, right, ladies? And I change it to an equation by inserting a k value, and then I flip the fc and the t. That's all I've done. Here's the formula that, in a sense, you have derived by doing that experiment, by coming up with shapes. And I've guided you through this. With me so far? Sort of, kind of? That's the formula that you've sort of come up with. There's one problem. You can't use it. Why not? First of all, you measured FC in what? Number of washers, not newtons. You measured mass in number of stoppers, not kilograms. And did you measure time in seconds? You did. So your units don't really jive here, right? They don't work. And we haven't put any numbers in there to figure out k. Do we need the value k to make the formula work? Yeah, just like you'd need the number pi, 3.14. If I never told you 3.14, you wouldn't be able to do area and circumference products. I need to tell you what the letter k stands for. What's the number? It could be 6, 47, 6.67 times 10 to the minus 31, 1.6 times 10 to the minus 19. There's one you know. Millimeters. Do you think k has a pi in there? What leads you to believe that it has a pi in there? To start. Pi is likely involved, right? Okay. So what I'm going to do now is we're going to move towards finding a value for k. So Fc equals krm over t squared. If you compare that to our old favorite F equals ma, what do the C's stand for here? No, centripetal. Centripetal force is equal to mass times centripetal acceleration. So we're going to predict, based on this, you see the m right there? If you get rid of the m, AC should equal what? KR over T squared. We're predicting that the formula for centripetal acceleration is KR over T squared. That's our predicted formula for AC. We're going to attempt to derive a formula to see if it matches our prediction and to determine the value for K. We're going to end up going towards that without the graphs. We're going to do it from a purely theoretical, what we know about circle standpoint.
Do we write that one down?
Sure. You write down predicted formula for AC, centripetal acceleration. Here's where your mind starts to get blown if it hasn't happened already. Mind blown yet? Yeah, it's okay. Do not, at the end of the day, expect to walk out the door getting all of this or being able to derive this or regurgitate it. Don't expect that. Just sit back and enjoy the beauty of the mathematics. Really. And sort of kind of get what I'm talking about. If you're good with that at the end of the day, I'm good with that. Oh, you will have to use the formulas at some point, though, right? Which I will give you. Okay, there's our predicted formula. Okay, let's talk about what we know about circles. In one complete revolution, the distance traveled d is the circumference. True or false? True, right? Circumference. It goes all the way around. That's called the circumference. You know that. The circumference of a circle is equal to 2 pi r. You were probably taught that grade 8 maybe. I don't know. Something like that. Period is the capital T. For some reason they use big T for period. It means once around. So what's going to be the speed? Well, speed or velocity, I'm taught you, V equals d over t. What's the distance traveled? Circumference, 2 pi r, period is t. So the velocity of the rubber stopper is 2 pi r over t. Big whoop, Mr. Bennett, who cares? I'm going to rearrange that. Instead of v equals 2 pi r over t, I'm going to take the t and the v and I'm going to switch them. And I'm going to write t equals 2 pi r over v. And I'm going to label that equation number 1, because I'm going to come back to it. The period, now, so in other words, if I told you, if you measured the time that it took for one revolution, and you knew the radius, you could figure out the speed of your rubber stops, right? You could have used that to figure that out. Okay, good. I'll pause there for a second. Let's continue. Centripetal acceleration. Do you know that the formula for acceleration is A equals delta V over delta T? You do. Can I rearrange that to delta V is equal to A delta T? I can. And for an entire period, I'm going to substitute delta T. I'm going to replace that with big T because that's period. And delta V, I'm just going to put another subscript in there. I'm going to say delta VT, total change in velocity. In other words, I want to know the total change after it goes all the way around, not just part of it. And I rearrange that to delta VT is equal to A times big T. And I'm going to call that saved equation number 2. And I'm channeling all this towards that idea of coming up with that value for K. And I promise I'll get there. I'll give you the ones at the end. I'll tell you. Don't worry. I'll put a star. I'll say, you got to know those. You're still in the appreciation stage right now. I don't know. I'll let you know. I'll call your name. Okay. Here's my least favorite slide in the entire course. Another way to think about, do not write this down. Another way to think about delta V for a whole revolution. Suppose several instantaneous velocities are recorded. The velocity right there is equal to V1. Tangent, right? The velocity right there is V2. The velocity right there is V3, and so on. And each one of those vectors would be the same length. Why would it be the same length?
Oh.
Because the speed is constant. Only the direction changes. The speed is constant, and the speed is the length of the arrow, right? Okay. This value in red, delta V, is the difference between V1 and V2. So this is the change in those two velocities. This is really V2 minus V1, and we can get into vector subtraction or what have you, but it's that vector there, right? And this one is the difference between V3 and V2, and I could go sort of all the way around the circle if I want. You can imagine that, I'm sure. John, pay attention, man. Get off the phone. Now, if you placed V1 to VA, all of those tangent velocities, if you placed them all tail to tail, this is what you'd get. There's V1, there's V2, there's V3, there's V4, and so on, right? And I haven't taught this yet, but vector subtraction can be shown as tail-to-tail vector arrangement. And these red guys here are simply these ones again. Now, if I didn't just take 1, 2, 3, 4, 5, 6, if I didn't take just 8 tangent velocities, what if I took 360 tangent velocities? Well, I'd have a lot of these little blue arrows pointing off here, right? And I'd have a whole whack of them here, and the red guys would be really small, and they would, for all intents and purposes, form circle. And what would be the radius of the red circle on it? Right you are. The radius of the red circle would be the black, 360 of these black ones, which is the speed of the rubber stopper thingy, right? And you could also say the total change in velocity, delta VT, the total change would be the sum, vector sum, delta V1 plus delta V2 plus delta V3 plus so on, all the way around. And because this is now 360, it's really kind of a circle, circumference, total change in velocity is 2 pi r, where r is those black velocities. Pause for dramatic effect and to let it kind of soak in, hopefully. Not easy stuff. It's probably taken me about 4 years of teaching 8 different times to be able to confidently teach that and say, yeah, I know what I'm talking about. Most kids have that look on their face. That's okay. No, it's going to get a lot easier. Don't worry. I'm just showing you where the formulas come from. Formulas don't just go poof and come out of nowhere, right? They don't. No, someone does this stuff. And one of the course outcomes is for you to gain an appreciation for that. Can I measure it? No. I'm not even going to try. Sit back and enjoy the beauty of the mathematics. So, delta VT from 2 pi r is 2 pi v. Why v? Because, as Adam said, the radius of this red circle is the black one, which is the initial velocity, 2 pi v. That's saved equation number 3. I promise you I'm not going to save any more equations. We're going to start putting them back together again. I have saved equation number 3. I have saved equation number 2. And I have saved equation number 1. And we're now going to put them together.
So this is the one.
Whoops. Getting there. Getting real close. Recall equations 2 and 3. There, I just put them on the screen for you. Delta VT is AT. That was equation number 2. And the latest one, delta VT is equal to 2 pi v. You'll notice that both of those equations start with delta VT. Total change in velocity. Which means that this AT must equal that 2 pi v. And so I set them equal to each other. And then I get rid of the t on the side and I write acceleration, is 2 pi v over t. I lied, I said I wasn't going to save any more. That's equation number 4. I took 2 and 3 together, because they both equal the same thing, and I created this, equation number 4. Are we having fun yet?
Is the v on 2 pi v, so is that just
That's the speed. Yep. Equation number 4. This was equation number 1. Do these look at all sort of, kind of, like they're something similar about them? I got an A, 2 pi v over t. Here I got t, 2 pi r over v. I'm going to substitute equation number 1. This one here is going to go into this, because it's equal to t, goes in there. This that I circled in red is equal to t, which I'm going to then place in there for t, because the t is t, right? And what am I going to get? A mess, right? An ugly fraction mess. You know that's coming, don't you? Here's what it looks like. I'm going to take that 2 pi r over v, and I'm going to stick it in there, and I get 2 pi v over 2 pi r over v.
Is this important or not?
I'll tell you. Don't worry. I'll tell you. I took this value for t and I plugged it in there and I got 2 pi v over t, which is over 2 pi r over v. Is there any canceling to be done there?
Yeah.
Well, yeah. 2's and pi's? What about those v's?
No.
Well, one is a v and the other is an over v, right? And how do you do that whole divide by a fraction thing? Remember? It's going to flip and multiply. So v divided by r over v is v times v over r. Now you multiply across, and what do you get for a? V squared over r. V squared over r. That's the one you write down. After all that nonsense, it boils down to the centripetal acceleration is equal to velocity squared over radius. That seems pretty simple, Mr. Bennett. The formula, not to get into it, right?
Yeah.
I'd be a fool to think you could do that on your own. I couldn't even, after I've taught this for as many years as I've taught this, if you gave me a blank sheet of paper and said, derive that formula, I couldn't do it without some notes. I don't expect you to.
So that's centripetal acceleration.
That, my friends, is centripetal acceleration. V squared over r. What does V stand for?
That's-
Velocity
Oh.
in meters per second.
I want that.
R stands for radius of circle in meters. A stands for centripetal acceleration in meters per second squared. And t equals the period in seconds.
Don't see it there.
Oh yeah, you're right.
We don't need T, or is this supposed to be T? Don't look at that, no. Anyway,
I have something else to show you.
let's just stay there.
No.
No.
I have something else to show you, because there is an alternate formula. It's like an alternate ending to a movie.
No, I
You know, when you buy it from the DVD and you get the alternate ending, the ones that are stupid and you don't like,
Yeah.
sometimes they're better than the real one, right?
No, not really.
Never are? Well, that's why they're the alternate one, because the director said, yeah, that was stupid, let's not do that.
Exactly.
There is another way to take this and come up with something different that includes t. Because do you ever think you're going to need t? Yeah. I think you sort of have that gut feeling that, yeah, sometimes they're going to give you the time, or you're going to measure the time, or whatever. You need one with t in there. So in other words, I want one with t. So now I've got 2 pi v over t. Can I take, this is 2 times pi times v and then divide by t. Could I go 2 times pi, divide by t, and then multiply by v? Why not? You can do that, right? Like if I went like 2 times 3 times 4, divide by, I don't know, 6, that'd be 2 times 3 is 6, times 4 is 24, divide by 6, well, that's 4. Could I go 2 times 3 is 6, divide by 6 is 1, times 4, same thing, right? Okay, so what I'm saying is, this can become 2 pi over t times v. Take the times v out. Okay? Leave the t in there. Because here I got rid of the t, I want to keep the t.
So that's it?
And the reason I do that, Hannah, is because v, from way back at the start, v was equal to, remember the velocity? It was the first one we did. Velocity was 2 pi r over t. That was equation number 1, I think. Equation 1, let's check. Right there, T equals 2 pi r over V, right? Which was, same thing. So, what does this boil down to? Can you cancel anything? You only cancel top and bottom, right? So it's 2 pi times 2 pi r all over T times T, which is 4 pi squared r over T squared. That might be the ugliest formula you've ever seen. 4 pi squared r over T squared. You're not doing calculations with that in your head. How many people were shown the magic triangles among grade 9 science? So, anyone been in a science class where they show the magic triangles? F equals ma, right? And the reason that I say to teachers, please don't show the kids that are going to be in grade 12 physics the magic triangles, because if you rely on magic triangles, how the heck are you going to solve for r there? Good luck. You're going to need a magic rhombus of some sort. Go ahead. So that's kind of why we need the T. I will caution you with this one. Students like to write, because you're used to saying or writing pi r squared, right? Do not write 4 pi r squared over T squared. Do you see how you can make that mistake? Okay, it's 4 pi squared r over T squared, not pi r squared. Don't make that mistake. Those are the two formulas that you need. If you have written nothing down, write those two down.
So you're gonna print them off?
I can do that. But you probably want those for your own piece. I'm not going to print them, I'll post them. You need those. V squared over r and 4 pi squared r over T squared. They both are for centripetal acceleration.
You have to put that AC was 2 pi by T times 10 and you just put the 4 pi squared.
Well, you would write A, centripetal acceleration, A equals 4 pi squared r over T
You
squared.
just square the whole thing. So.
Oh, the squared here is just a pi.
No, the square, with your square that you made the square over.
Oh, yeah, no, sorry. Yeah, oh, I see what you're saying, yeah. No.
Yeah.
Gotcha. Okay, now, I have to give you a little bit more. This is relatively simple if you I know, you'll be fine. I bit off a lot here. I could see the look on, I could see the look on your face. What was our predicted formula from that experiment that you did? Remember the one with the K in it? Yeah, it was A equals KR squared over T squared. Oh, I said T, didn't I? A equals KR over T squared. What's the value of K now that you know this? This is the formula that we got. What's the value of K? The value of K is 4 pi squared.
You have to write that down?
Which is what?
Does that matter to us?
Well, you're getting it. You've already got it, Hannah, because I told you to, right?
But do you have to,
Listen.
but do you have to write down that that could also equal K, or is that?
No, that predicted formula was, we were using that to drive our thinking towards the front. If we derived that, you would have seen it, right? That's why we had to do that one, so that we could figure out what the K value is. Should you be shocked or surprised that pi is involved in the K value? No, of course not. Is it a magic, like, do we take pi squared and multiply it by 4 and memorize that number? No, we just write 4 pi squared. That's the number, 4 pi squared. Don't worry about what it is equal to.
140 something.
Yeah, 3.14, 3 squared is about 9 a little bit, maybe 10. That's what's about 40, right?
Like 4 times 3.14 is like 12.
No, but only the pi is squared. Only the pi is squared. Okay, now, one last little bit, because we also want formulas for centripetal force. Force is mass times acceleration. Here are those two again. Please don't write them down again. You've already got them. Right? Given these, if we want a formula for centripetal force, how do you take acceleration and make it force? Well, F equals ma. Heather, stick with me here, please. Put it down, please. Try to go more than half an hour without picking your phone up. F equals ma. FC is equal to mac. Is this not equal to A? How do I turn this into force? Anyone? Right? Bingo. You simply add the m to the formulas to turn the acceleration into a force. He's absolutely right. This is equal to A, right? If F equals ma, that A is the same as that A, put an m in front. So if you want this to be force, you put an m in front. If you want this one to be force, you put an m in front. And it looks like this. And those are the ones you want to write down. Those two right there. Centripetal force is mv squared over r. You will use that a lot in the next week and a half or so. mv squared over r. And putting an m in front of the other one, m4 pi squared r over t squared. Say that real fast 10 times. No, don't. It's hard enough to say once slow. m4 pi squared r over t squared. I hope someday I can forget that point. Second one. The first one I don't think I'll ever forget. I've used it far too much. mv squared over r and m4 pi squared r over t squared. That is ugly. No doubt about that. Do I have anything else here? Oh yeah, I got this guy. I had a sweater like that once. I wore a sweater like that once. Yes, Hannah, I did. Someone always asks that too. Is that a picture of you, Mr. Mitch? I had a sweater like that. It was the 80s, you know. Yeah. That looks like me? Yeah. Actually, when I Googled for nerd looking at, I'm using that one. That looks like me. Some kid said that to me after I was growing up. Mr. Man, I feel like I've been going in circles. I appreciated that. I can't remember who it was. I should have put their name in here. I remember. Yeah. I don't know who that was.
How long ago was it?
Oh, that picture's been there. That picture's been there a long time. Like, look at it. Yeah. Long time. Here we go. Sample number 1. An object of mass 1.5 kilograms tied to the end of a string 0.5 meters long and swung in a horizontal circle with UCM such that it makes 5 revolutions per second. Find the frequency, period, speed, the centripetal acceleration, and the tension in the string. I have not yet talked about frequency. What does frequency mean?
How often?
How often? It's how many times per second. Frequency is how many times per second. So it goes 5 times. It goes 5 times in 4 seconds. I'm having a hard time here. So what is the frequency? 5 divided by 4, or 1.25, right? 1.25 what? Do you know? What's the unit for it could be, you could write it as revolutions per second, but the correct unit for frequency is hertz. HZ. Hertz. If you look at your computer, it doesn't talk about megahertz anymore. That's so big. But gigahertz. If you look at a really old radio from an old car, it'll show like the radio frequency in megahertz, kind of thing? Yeah. Hertz is the unit for frequency. It's the opposite of period. Here's a formula that I didn't derive for you. I'm just going to give it to you. I am the formula God. This shall be the definition of period. T is equal to 1 over F.
This is a period formula?
This is the period formula. T is equal to 1 over F, or you could write that as F is equal to 1 over T. They are said to be inverses or reciprocals of each other.
1 over F?
1 over F or 1 over T. F is frequency, T is period. So the period in this case is 1 over 1.25, which is really 4 over 5 or 0.8 seconds. You should be able to, it's kind of like the kilometers per hour, meters per second thing. If I give it to you in seconds, you know it's period. If I give it to you in hertz, you can convert it if you need to. It's just a flip. Okay? So T is equal to 1 over 1.25, which is 4 over 5, or 0.8 seconds.
Wait. That's it. You equal
No,
to
8 seconds.
How'd that come about?
If frequency is 5 over 4, period is 4 over 5. It's just the reverse, it's the flip. Okay? A little bit of practice and you'll get the hang of it, no problem. Okay, part C. This is part A. Part B. Part C, the speed. Do you remember? I didn't really box it up for you, the speed one, but do you remember from the very first equation?
V equals, U over
No? V, remember, is distance over time,
Oh,
2 pi r over t, right?
we just remember these because we're putting these down, but we weren't
You-
supposed to write them down.
Yeah, I apologize. That one you should probably write down. That one, you're going to need that one.
What's that one?
Okay,
2 pi r over t.
the one's supposed to be speed?
Yeah, 2 pi r over t.
It says the speed.
The speed is the distance, which is the circumference, 2 pi r, divided by the time. I apologize for not saying right that one down. 2 pi. Now, what's the radius of this thing? The string is 0.5 meters long, so my radius is 0.5. And my period is this 0.8 value that I just came up with. So the speed here is 3.93, I guess, right? 3.93 what? Meters per second. Good, relatively okay. A little bit new, but you'll get it. What am I asking for in D? AC, centrifugal acceleration. It says two different ways. I just want to point out that you could either go A equals B squared over R, 3.93 squared over 0.5, or if you really wanted to have some fun, 4 pi squared R all over, no, 4 pi squared R all over T squared. See how much fun it is? Would they give you the same answer?
Yes.
Yes, they would. You don't have to solve that one. Just be aware that you could do that one if you wanted. So 3.93 squared divided by 0.5. 30.9. 30.9 meters per second squared. Does that seem like a relatively large number? Does that seem like a big number? It does a bit, doesn't it, right? How come? It's because you got to change the direction. There's a lot of force being applied to changing the direction. You're going to get the same number over here. Almost there. I apologize for the longevity, the length of this, and how tedious it is. Just the way it goes. I used to say physics notes were like bananas. Yeah, because they come in bunches. I don't say that anymore because people think it's lame.
Okay, let's do E.
E, tension in the string. What is tension? It's really a force, so I'm asking you for the force, right? Fc is equal to mv squared over r, which is really just this number here, right? So it's the mass. What was the mass? Oh, way up. 1.5. So it's going to be 1.5 times 3.93 squared. And the radius was 0.5, I think. $46.3-ish? 46.3 newtons. Not that bad. What I'll do on Monday is I'll just review that kind of thing so that you've got it fresh before we move on with the next one, and then I'll give you some time to work on Monday on that.